So there's a couple more ideas we need to discuss, and really we're going to conclude this section and hence the chapter with something called the rank theorem, which is actually a nice little result, and its main beauty comes from the fact that it's so simple to state, but yet it has so many complex ideas built into the notation. But we just need to state a few things before we can do that. So I'm going to state another theorem, and this theorem is not really a mystery. I think most of you might have guessed that this is true already if you've once you play around with a couple of these problems, but I'm going to state it anyway. For any matrix A, well, ask yourself the following. How many vectors, like let's go back to the matrix A for a moment. How many vectors are in the basis for the column space? And you'd say, okay, there's 1, 2, 3, because we found the basis over here. There's 3 vectors. Well, why is there 3 vectors? Let's try to dig a little deeper. Well, there ended up being 3 vectors in the basis for the column space because there was 1 vector for every one of the leading ones that showed up in the row echelon form of A. We went up and took these columns instead up here, but still the number of leading ones in R told us how many vectors we were going to have in our basis for the column space of A. How many vectors do you think would be in the basis for the row space of A? Well, how would you have adapted your technique? Well, we did this in the previous example, but it's just not on this page. To get a basis for the row space of A, we took the rows from R that had leading ones. In other words, there's 1 row for the basis in the basis of the row space of A for every single leading one that appears in R. So there's the same number of leading ones in R, no matter whether you're looking for a basis for the column space or a basis for the row space of A. So that, with that in mind, this shouldn't be surprising. Because remember, the dimension of a subspace is the number of vectors in a basis for it. So here's the statement. The dimension of the row space of A is equal to the dimension of the column space of A. So that is the theorem we're going to state, and that justifies why the following definition makes sense. And do I have enough room? I'm going to slide this up a bit. So we're going to define something called the rank of a matrix. So let A be any matrix. Don't even have to say M by N, because we're not even going to refer to M or N. So the rank of A is just to define to be this common value. Whatever the dimension of its row space is, and hence what the dimension of its column space would also have to be, whatever that common value is, that's what we're going to define to be the rank. So the rank of A is given by, well, the way we write it for notation was we just write the word rank, and then you write A in brackets after, and you just say it's equal to, you could choose whatever one of these you like better to write down. I'm going to use the dimension of the row space of A, but you could just as easily have written dimension of the column space of A. Both of these would work. What you're essentially doing is the rank of a matrix A. This is the idea that it captures. If you were to reduce A to reduce row echelon form, in fact, row echelon form would be good enough. But if you did reduce A to reduce row echelon form and you counted the leading ones, the rank of A is what tells you how many leading ones there's going to be. So this is equal to the number of leading ones which appear in the reduced row echelon form of A. So that's an important note, which I decided to put it in green just so it stands out a bit, because that's a really important thing. If you want to know what is it that you're actually talking about here, this is how you would say it. But notice how much briefer this is to write down than that long sentence, right? It's just so much more direct and concrete, and it's not dependent on being able to articulate it clearly with ordinary language. You can say it in symbols very briefly, as long as you know what dimension means, and you know what row space means, and you know what column space means. Or in fact, if you just knew what one of those are, you don't even need to know what the other one is, because they're both the same, so knowing one would be enough. But that's the definition of the rank, and this is the idea that it's really capturing. Okay, we'll also define something called the nullity. The nullity of A is given by the dimension. Actually, and the notation that I use is just you write the word nullity, you put A in brackets afterwards, and then what it's defined to be is the dimension of the null space of A. Okay, so remember we mentioned at the beginning of this section, the null space of the matrix A is just simply its solution space. So we talked about how to find a basis for the null space of a matrix in the previous section, and really what it comes down to is you're going to have one vector in a basis for the null space of A for every single parameter that you need when you solve the associated homogeneous system. So let's actually, there's a nice interpretation of the nullity as well, which I'll include here. So this is equal to the number of parameters that you would need to write down the general solution to the associated homogeneous system. And I'm just going to write it down in the form of a matrix equation. AX equals 0. So these two notes are really important because they tell you what you're actually calculating if you work out the nullity or the rank of a matrix. Okay, and in fact, once you accept that these notes are true, and once you calculate the rank of a matrix and you calculate the nullity of a matrix, all you have to do is do it once on your own and you'll instantly be convinced that these notes are true, because you basically have to encounter these ideas along the way to calculating the rank or the nullity, and then you'll instantly see the connection. But it may take you working through one on your own to get it, or to see that connection. But once you do that, the rank theorem will not shock you in the slightest, which is what I'm now going to state. And this is actually going to be our final thing. Because how do you choose think about this, how do you choose which variables are going to have parameters when you solve a system like this? Well, you'd write out the augmented matrix, you'd row reduce it as much as you can down to reduced row echelon form, and then you would assign parameters to all the variables that don't have leading ones. So every column either has a leading one or that corresponding variable gets assigned a parameter. So it shouldn't be a surprise that the number of parameters that you need plus the number of leading ones that you get in the reduced row echelon form of the matrix A, those two numbers are going to add up to precisely the number of columns of the matrix A. So that's really what the rank theorem says. So let's start with a matrix A and let it be M by N. Then, like I said, the beauty of the rank theorem is just how simple it is to state. If you listen to what I said just a moment ago, you might have, it's really easy for your head to spin because there's just a lot of words and it's a very long-winded phrase, but the rank theorem just says it so briefly. It just says that the rank of A plus the nullity of A is equal to the number of columns of A. That's so brief compared to how I said it the first time. And in case you forgot what I said the first time, let me say it one last time just to give you an idea of how, or give you a reason to appreciate how brief this is. But if I were to say this out loud in words without using the words row space, column space, or dimension, I might say the number of leading ones in the reduced row echelon form of A plus the number of parameters needed to solve the associated homogeneous system to the matrix A has to add up to the number of columns of A. That's quite long-winded and awkward to say, and if you're not listening very carefully, it's easy to lose track of what's being said. Whereas this is just so brief and clear, that's where its main attraction is.